Okay, good morning, everyone. We're in the Fortran Kokkos interop section, but this is not really about interop. This is about replacing Fortran with Kokkos. This is something me and my colleague Joey Pate work on at the lab. At the lab, there are a bunch of actively developed Fortran codes and legacy codes. And to get them running on the GPUs, we're just going to port them right to Kokkos. So one such code is flag. It's a multi-physics code. It has a lot of interesting physics, and basically the task is do all the same stuff, but now on the GPUs. And so flag is about 30 years old. It's mostly Fortran 77, but in free form. What we write in flag is not actually Fortran. It's an extension of Fortran that includes some domain-specific stuff. But when you look at it, it pretty much looks like Fortran 77. There's some really old C laying around, and thanks to some of our efforts, there's now some C++ 20 for fun. I went and counted all the subroutines and functions defined in all of the languages, and as you can see, there are 95% of our definitions out of about 14,000 are Fortran, and that's perhaps a reflection of the people who work on it. We have around 20 active developers. Most of them have a great wealth of Fortran expertise and varying C++ experience. So our strategy for getting on the GPU is to use Kokkos. The machines that we have unified memory, so we're going to use it. Christian told us that's a porting crutch. I agree, but it makes our life easy. On top of Kokkos, we've developed a rich abstraction layer. We call that Locos. This is basically making Kokkos and C++ look like Fortran, so our developers can read and write ported code without much training at all. Another key pillar of our strategy is automate as much of this as possible. No one wants to spend their career writing 13,000 functions or subroutines entirely by hand. So this talk is going to be basically how we make it into C++, how we parse things. So I just wanted to give a quick example of that. So here's a silly little subroutine. It takes in a double, and then we increment it by 1. To make this run on the GPU, we rip out the contents of the subroutine and basically put in a branch point. If your build has a GPU, then what you'll do now is call a new version of the subroutine, and if it doesn't have a GPU, then we'll take the previous implementation, append an _f to it, and slap it right below. That new subroutine is in a module. There's an interface out to C. The types of all the arguments are converted to their C type. We're finally now in C++. We write our extern C, take in our C type arguments, we wrap them into views, and then pass them to an implementation. And then we increment by 1, but now on the GPU. So this is all the boilerplate that you need just to get to here to finally do the compute. So we developed the tool called the locoifier to do all of that for us. Its job is take in a Fortran subroutine name and then automatically generate all of that boilerplate code that gets you out into C++. And this means our developers can then focus on writing performance portable C++ implementations, so writing kernels, not writing interface. We think this is a good idea because writing all the interface code is terrible. It's just rewriting redefinitions of things to make it through a pass-through layer. At the end of the day, it gets you across the language boundary, nothing else, no compute. And when you do it by hand, it's incredibly error-prone, so it's a fantastic thing to try and automate away. The locoifier operates in 4 phases, the first of which is find the subroutine, read it, parse all the information out of it, and then write all of the interface code that I showed you before. And the rest of this talk will be a deep dive on exactly how we do that parsing, and then we'll conclude with some examples of it being used on increasingly complex things. So to understand what's going on, it's informative to look at a flag subroutine. So here's one called split KC constrain. And we can loosely assign to the majority of the subroutines in flag a structure. So at the top here, there's a comment. This is really a comment to the developer, which describes how you invoke a call to this thing. There's then the subroutine signature, that is the name, the list of arguments. If you're lucky, there's a descriptive comment of what this thing actually does. Then there's some Fortran variables that get declared. One of the domain-specific extensions of Fortran that we've included is an interaction with a database. So the syntax for doing that is access, database handle, all the data I want to get from the database. And then typically, after you have declared everything and gotten it all from the database, you'll then do some compute with it, and we just call that the work section. And to parse this, we use something called Antler. Antler operates in two phases, the first of which is called the lexing phase. Here, it reads the text that you supply it, and from that text generates a stream of tokens from a set of lexer keyword rules. So I'm going to make a language analogy here. These keyword rules are essentially a dictionary of words that we've told Antler, hey, pay attention to these things. So we have our database interaction, which is access. In Fortran, there are do loops. There's if, else, then, subroutine, all the end versions of all of those things. We have all the types, and then we have to deal with strings as well. After the stream of tokens is generated, it's then consumed and stitched together in something called an abstract syntax tree according to grammar rules. So this is, to continue with the language analogy, how do we string together the words in our dictionary to form sentences? So if you had something like a function, it would be name equal name, and then open paren, perhaps a list of arguments, and then close paren. And if you recall our subroutine definition from before, it was something like split case C constrain, open paren, list of arguments, close paren. This is just a visual representation of the two things you saw before, but now in the syntax tree. And what you can do is stitch together these grammar rules to reflect the structure that you want to capture. So to continue with the language analogy, now that we have sentences, we're going to tell Antler how to begin to construct meaningful paragraphs. So we do that, and it essentially reflects the structure that I showed you before. There's a subroutine that's a function statement, then some variables, then some accesses, and then the work section. And what you can do is slurp up all of this metadata, put it into a Python class. Here it is for split case C constrain. We have the signature, the arguments, all the things that got declared. And we have all of the information about all of the data that was used there. So with this and our abstraction layer, you can easily generate all of the interface code that you need to make it across the language boundary. And you might notice that there's no purple section here. We're not actually capturing in this parsing phase the work that went on in the Fortran subroutine. And it turns out that this is a rate-limiting step for our developers. So we're beginning to consider having the low-codifier do more of this. We've been generating interfaces for on the order of, say, 2 years now, but want to get more out of our tools. And the problem with doing this in Antler is that parsing Fortran is hard. So if you had something like B, open paren, C, close paren, it's impossible to tell if that's an array access or if that's a function. If you have something like A is equal to B plus C, it's also impossible to tell, is that arrays you're adding together? Is it a bunch of ints? Is it a bunch of reals? So on and so forth. There's also implicit typing, so if your variable begins with a particular character, then it's typed in some way. But another thing that's particularly challenging is continue statements and labeled do loops. So what that looks like in Fortran is do, integer label, iteration I, lower bound, upper bound, some stuff, and then undo. And if you're to write a grammar rule for this, it looks something like do int id equals expression, comma, expression. And the problem with this rule is that it looks exactly like an assignment until you see the comma. So this could be do 10i is equal to some value, or it could be a labeled do statement. So you have to do something called a look ahead, and this is also hard to do in Antler, and it's basically the land of edge cases. But the good news is that our compilers are already doing this for us, and they're doing it really, really well. So we're thinking that we'll just take the compilers and hijack them. So Flang is one such compiler. It's LLVM's modern Fortran front end. It reads Fortran, creates a syntax tree, and then ultimately lowers everything into machine code. Flang's parse tree is a complete syntactic representation of the source program. It directly reflects the Fortran grammar. It's written in C++. It uses std-variant-based node types. It preserves the source location and the structure of the code. And it can be traversed, this AST, the tree, using a visitor pattern. And we can actually hijack that visitor pattern to collect the information that we need as Flang works. And there are a few ways to do this. So on entry to a node, there's something called the pre method. It fires when you hit the node. You can tell this to continue to traverse down the tree. Don't go any further. Switch to a different node. Once you're at a particular node, all the alternatives for things are encoded using std-variant, so they have a visitor pattern that you can write. Okay, I'm going to visit decltype.u, and then if I visit an intrinsic type spec, I must be something like an integer or real. If I'm a type, I must be a drive type. If I'm a class, I'm a class, and you can do a catch-all. So this is just a little bit showing how we navigate this AST and actually get the information that we need from it. The things that we collect from that AST are declarations. So what is your type? If you're an array, we need your rank and shape. In Fortran, there are attributes like allocatable, pointer, parameter, so on. We collect all of that. We collect the control flow, so that is do loops, if, else, that sort of thing. And we also keep track of the scope hierarchy. So basically, at every scope, we record every event that happened. Other events that we keep track of are mutations. So if something is passed as an argument to a call, we assume that that thing can do whatever it wants to it, and so we mark that argument as mutable. For assignments, we keep track of left-hand side and right-hand side, and we build expression trees from that. We keep track of things that are allocated, and we also encoded into Flang how to do our domain-specific database interaction. And so you may think, okay, if you recorded every event that happened at every scope, you have all the information that you need. You now just need to translate it. The problem with that is that it would write really bad C++ and even worse Kokkos. So one example of that is declarations in Fortran. In Fortran, all of them have to be at the top of the subroutine, program, or module scopes. That's really bad practice in C++, so you could have something which must be defined in Fortran up at the top and then use it 1,000 lines later. We don't have to do that in C++, and we shouldn't. So to make to translate this just directly without doing any syncing, you'd have everything declared at the top, and then you use it. After declaration syncing, you don't declare things until they're used, and if they're only assigned to once, you can also mark them const, which is great practice. I'm going to skip, in the interest of time, exactly how we do all of this stuff and just provide descriptions of what we're attempting to do. The other thing we have to handle is parallelization. So we could just say, okay, if it's a do loop, it's now a par4. That's a really bad idea, in particular in the case of reductions. So Fortran loops that accumulate scalar values need special handling, right? If I just naively parallelize this over I, I'd get a race condition. Thankfully, Kokkos parallel reduce just handles this automatically. So we just have to look at our event list and attempt to determine that scalar is modified in a reduction-like way. The other thing that's kind of tricky here is that we have to ensure that such scalars are not used as an accessor within the scope of that loop. Another reduction we have to pay attention to is things that reduce through indirection. So Fortran loops with indirect array writes can create race conditions if naively parallelized. So suppose we parallelize over S, we use S to get some other value through this map, and then we use that other value to write into this array CSRF. You could imagine that many S's may share the same C1, and so you'll have a potential write conflict here, and life will be bad. Thankfully, Kokkos has scatter views that provide thread local copies with atomic or duplicate-based conflict resolution. So You just wrap the underlying data in a scatter view, access that scatter view, do whatever you need to the data, and then at the end, merge your thread local copies if you need to. And so we need to detect this kind of pattern in order to parallelize. In Fortran, there's not asynchronous execution. There's no idea of execution space. So we could end up in situations where we parallelize something and then another kernel relies on that data being written to. So we need to pay attention to fences. Therefore, we try to keep track of host and device rights. Again, I'm going to skip over how we do this and get to the examples. So here's one. This is in our unit test. Declaration syncing. Let's pay attention to scale here. So on the Fortran side, scale has to be declared up here. It's not used until down there. It's also assigned to wants. After we run the local codifier, so the C++ is on the right. I've omitted all the interface stuff because that's boring. You see now scale is not declared until where it's used, and it's also marked const because it's assigned to wants. The same thing is true for temp. The next example is scatter and reduce at the same time. So here we iterate on S. We use S as a map into some other ID, use that ID to write into an array called target. And then at the same time, just to be tricky, we're going to do a reduction on total. We detected that the reduction on total is going to happen, so this thing becomes a parduce when translated. And in route of the reduction, we're also going to wrap our target in a scatter view. We then access it, we do what we need to it, and then we remember right at the end, contribute thread local copies if they exist. This is a horrible nightmare, but bear with me. We'll try to get through it. This is our fence example. So the first kernel here writes A into B, then B into C, then there's a reduction on B, then C into D, a reduction on C, and then a host access right at the end of the reduction value on some C. So between the first and the second kernel, we have a device execution space fence inserted because B was used in writing C, so we need it, the first kernel to complete before we actually do this. In between the second and the third, there is no fence because we already have B. Between the par reduce and the par 4, we inserted another fence. No fence here at the end. And finally, at the end, because we need the reduction, and I can never recall the Kokkos rules on whether or not they're blocking, we inserted a fence everywhere. So all execution spaces must meet at this point before we do this final host write of final result. Okay. A constant theme through this entire effort is why not just use AI to do this? So I wanted to talk about that. Back in late 2024, I gave, I want to say Llama 3B, which admittedly wasn't that great at the time, even at the time, the low codifier example and just said, translate this to C++. And it was like, okay, I can't convert real kind 8 to some corresponding C++ type, so I'm just going to make it const char star. And then it wrote a main, and then it initialized the input to this test function to hello world, and it's sized incorrectly. So really pretty horrible. At the time, ChatGPT 04 did great, but we had some questions on whether or not we should actually be doing this in the first place. Today, we were using AI paired with the low codifier, and even then, it does some things well, other things not so well. So in the first version of low codifier, we had trouble detecting whether or not things were actually mutable because we didn't pay attention to the work section. And you can see that the low codifier wrote in the interface that this variable here, BEMF, is const. It then was modified, and the compiler threw a fit about it. And instead of just removing const, Claude Sonnet 4.5, which is pretty up to date today, just made a local value of it and was like, okay, problem solved, move on. So this compiles, but it gives the wrong answer. So my opinion on using AI for this is if you can use deterministic scripts, you get a few benefits. It drops your token use. It reduces context window bloat. So they're really good at supplementing things. The other thing is that the localifier names all parallel fors and parallel reduces as loop, because it's really hard for me to determine what you actually do. So this would be a great place for AI to come in and actually assign a meaningful name to the work that went on in a particular kernel. So with that, I'll conclude and take any questions.
Okay, let us thank the speaker. We have time for questions, and we start here.
Thank you for a nice talk. Is it possible to make a locus direct in MLIR framework and make a translation in between Fortran IR to locus IR and emit locus code?
IR, I believe, it may depend at what point in the process, but your variable information is like erased, right? So you don't have meaningful names for your stuff anymore. The other thing is just directly translating Fortran into some other language, you don't get all the features that you want, right? You only had the features that were there in the original source, which is a subset of what Kokkos could provide. So you really want source to source. This is a starting place, and then you're going to go and change the C++ and do, the right Kokkos things.
So Flang is under active development at the moment. I was just curious, how stable is the AST access and transformation that you're using?
I can't really say. I've only been using Flang and this other stuff that we've developed for a few months. So far it's okay, but longer term I don't know.
And can you speak a bit more to it? Is it a bit like, I'm familiar with the Clang query / Clang tidy thingy and how you can, piggyback on the AST traverse to do stuff. Does it look the same?
No, I think it's entirely different. The file that's most informative to look at if you want to take a look is like parsetree.h or something like that. That's where all the types are defined. But I believe it's completely separate.
Yeah, thanks for the talk. So I'm also doing Fortran to C++ translation. One challenging thing I see in my daily work is that our Fortran code usually has like 200 arguments, which across many lines. And in the tool you just demonstrated in the slides, looks like you are really doing like line by line, source to source translation. Did you consider like refactoring all the data structure into like a strut or class in C++ and make it interface more C++ style rather than the Fortran style? Just like you said. And also, is this a open source tool that we can test, or it's internal to Los Alamos?
Okay, I'll do your second question first. Right now, this is internal. Most use cases don't require a refactor, but there are certainly a handful that do. So when appropriate, we will do that by hand.
Let us thank the speaker again, and let's see the next speaker set up.